Okay, so in the last class, we're discussing about classification of second order linear PD. So the generalized second order PD was considered as d25 dx2 plus b. This was our equation 1. Okay. And based on the coefficients b square minus 4ac, and this b square minus 4ac is nothing but a solution of a kind of a solution. It is like, if you have ax is equal ax square plus bx plus c, one quadratic equation, its solution comes like minus b plus minus under root b square minus 4ac divided by twice a. So based on the b square minus 4ac, your solution will have different roots. Okay. So x roots, number one possibility is that roots can be real and same. Another possibility will be real and distinct. And third possibility is that all imaginary roots. Imaginary roots. How many roots will be here? Two roots will be here. So two roots will be real and same, imaginary or distinct, or real and distinct, or imaginary roots. Okay. Now where this ax square plus bx plus c comes from? Okay. So that we were trying to see in the previous class. So we'll continue with that. So we said that let the curve, let C be a curve, let C be a curve, okay, in a domain omega, such that x, y with higher derivative, with higher derivatives along C satisfy equation 1, that above equation, this equation. And also we say let some quantities like del phi del x is equals to p, del phi del y is equals to q, and del 2 phi del x2 is equals to r, and del phi del x del y is equals to s, and del 2 phi del y2 is equals to t. Now from the differential equation, then along C, we know that these differential equations dp can be written as del p del x dx plus del p del y dy. This can be written as r dx plus S dy. Similarly, dq can be written as del q del x dx plus del q del y dy, and it can be written next is x dx plus t dy. And equation 1 with this let assumed PQRST, we get equation 1 as AR plus BS plus CT plus G is equals to 0. We have R, S, T. These are three variables, and we have now three equations. So we'd like to okay. So we eliminate R and T, okay, such that, so try to eliminate R and T. So R can be written as dP from this equation, equation number 2 and equation number 3. From equation number 2, R can be written as dP minus S dy divided by dx, and T can be written as P is equals to dq minus S dx divided by dy. Okay, so you substitute in this in
Sir,
the equation number 4. Ah, yes.
sir, in the last equation 4, what is G?
G is already coming from this, right? Okay, we'll write F.
Okay, sir. Got it.
So you have to arrange this equation. Our purpose is to get that equation, okay, that b square minus 4ac. So after arranging this equation, you can arrange it like this. So I'm not going to do those. I will just write those. Though derivation is not important, I just wanted to show you that it works like that. Okay, now multiplying by dy by dx, this above equation, you will get s minus a d2y dx dy dx plus b dy dx minus c plus a dp dx dy dx plus c dq dx plus g dy dx. Or F or capital F. Okay, then we choose S to vanish, choosing S to vanish. Then this A dy dx square minus B dy dx plus C is equals to 0. Now this equation, this is the equation. Uh, this term is 0, which also implies that this particular term, this last term is also 0. Okay. Uh, this is a compatibility condition for characteristics to be satisfied. This is called as characteristic equation. Now, from this characteristic equation, we know that dy by dx, it will have two solutions, 1, 2, and those can be b plus minus root b square minus 4ac divided by twice a. Okay. So, if b square minus 4ac is equals to 0, then b divided by 2a, they will be all, you know, they will be real. Okay, real and same. So dy by dx is equals to dy by dx. This is a 1 and this is a 2, second root is equals to same, b by 2a. So roots are same and real, and they're real. So this particular type, then that equation which we're satisfying along this C, and along this C we have got this characteristic. We say that that particular equation which satisfy this particular condition, okay, is a parabolic. So we say that this is a parabolic PD. That PD is a parabolic PD. If b square minus 4ac is greater than 0, if this value is greater than 0, then the roots will be real and they will be distinct. Okay, so dy, we will have two roots. One will be dy by dx, and we will have another root, that is dy by dx 2, and these are real roots, real and distinct, real and distinct root. Okay, in such cases the equation PDE will be hyperbolic PDE. Hyperbolic PDE. Okay. Third case is b square minus 4ac. If less than 0, that if less than 0 means it can be negative and this thing. So under root of negative will become imaginary number, and you can have dy by dx 1, you can have dy by dx 2, second root, and these will be imaginary roots. Imaginary roots. Okay, in such cases, the PDs are called as elliptic PDs. Okay. Elliptic PDs. So, what are the examples of parabolic, hyperbolic, and elliptic PDs that we are going? Okay, so what are these dy dx 1 and 2? These are also called as slopes, are also slopes of the required curve or line. Can say, okay, it is a curve or line or a surface. It can be a straight line, it can be a curve. Okay, depends on the type of the equation. So it is a required curve um, C along which higher derivatives do not exist. And the direction direction represented by the slope are called as characteristic. Okay, so based on this characteristic, we can also see that what type of equation they are. Okay, so let me just talk about parabolic PD. Okay, now this in this case your you know A is your alpha. Okay, and C is 0. So we get this condition b square minus 4ac equals to 0. Now, so in this case, all roots are imaginary and they are same. Okay, so roots are same. So number of roots, there are two roots, but they are same. So essentially only a same one root you can say. So what you will see in such problem that there will be one characteristic. There will be one characteristic. So like this. Okay. There will be one characteristic. Number one. Number two, the solution of this problem, now this parabolic problem, the solution of this parabolic problem, solution type of this archetypal, parabolic PD, del t alpha, del 2t, del x2 will be a diffusive type. Solution type will be diffusive. You have to remember. What does it mean by diffusive? Suppose this is your solution t as a function of x, okay, as a function of x. And at particular t is equals to 0, if this is a solution, if this is a solution at t is equals to 0, at any other time, the solution diffuses. Okay. Now here you have a higher peak and that peak is getting diffused. Okay, so it is trying to become flat at other times. So these are at t greater than 0. So as time increases, it becomes more diffusive. Okay. So that is the particular characteristics of this parabolic PD. Parabolic PD will always have this type of solution nature. Number three, the boundary conditions. For this particular problem, we have a x varying, and we have a time axis. So I am writing this as a x coordinate and this is a time coordinate. And then also I'm writing at the end showing the same time coordinate like this. And we know that there is a one characteristic. Okay. Now what are the boundary conditions we need to give? So del t, we have this del t by del t and del 2 t by del x2. So we need one boundary condition because del t to del t. So it is a first order with respect to time. So we need one BC for one BC. One BC means that is initial condition. One BC for time. Okay, that is nothing but initial condition. Second, we have a del 2 t del x2. So we need two boundary conditions, two BCs, okay, for x. What are two BCs for x? One BC will be its first end, first boundary and second boundary. So at x is equals to say 0, you need a boundary, and x is equals to L, you need another boundary. So here BC1 and here boundary condition 2 will need to be specified. Now at t is equals to 0, also you need to specify the boundary condition or initial condition or boundary condition at all x. At all x, you need to specify the values. Okay, so initial condition is specified for all these points. If it is a discretized domain, or if it is a continuous also, you can say that you need to specify all these continuous points initial condition. Okay, if it is continuous also, you can say all these continuous point, every point initial condition at t is equals to 0 has to be specified. Okay. So now this particular problem with these boundary conditions on time and space, you proceed in a forward direction. Okay, in the direction in which this characteristic is moving. So this characteristic will be keep on moving. Okay, it will be initially here, then you keep on moving. As you progress, you keep on moving. Okay, so you forward in a time domain, forward in a time. Okay, so you don't come back don't go in a reverse direction, but you go in a increasing time direction, and keep on calculating the next value. So this is equals to t is equals to 1, you will calculate t is equals to 2, t is equals to 3. You will keep on calculating the solution for such a problem with this boundary condition. Okay. Another characteristic with domain of dependence. Okay, domain of dependence and domain of influence. Domain of dependence and influence. Okay. Now in this case, uh, as I said, suppose this is a x domain and this is our time t domain, time t axis, and we have we are calculating say at this time. So we have this one characteristic, and suppose I want at this time, at this point I am calculating a value, then the influence uh, to this point, this ith point, is coming only from this particular part. Okay, this particular part. But there is no information coming from this side. There is no information coming from this side. Okay, there is no information coming from the top side. So domain of de dependence of any point on this line is this. Okay, domain of dependence of this ith point is only dependent from these values coming from the lower region. But above that, there is no value affecting this ith level value, ith point value. But this ith point value will affect any other point in the future. Suppose there is another time t plus delta t, then this point is going to affect. So the all the region above is called a domain of influence. This is a domain of influence. This is a domain of influence, and this is a domain of dependence. Now suppose you are designing a scheme where to calculate the ith level point, then you should only take the points neighbor points from neighbor coming from this. You cannot take neighbor coming from this. Okay, this will not give any result. So this is not needed. A neighbor coming from a neighbor to this neighbor is of no use. So while designing a particular scheme, you have to be very so specific. So scheme, design of scheme should be such that such that the point under consideration or the node under consideration has influence from the neighboring nodes or point or node value under consideration has influence from the neighboring nodes, node values coming from node values coming from the domain of dependence only. So we have again one thing is most of the schemes are forward in time. Forward in time schemes are used. Okay. And in such cases, stability may be a concern. Okay. Next is hyperbolic PD. Now, the example of hyperbolic PD is can be written like del square t del t square is equals to minus a square del 2t. There are variety of ways in which you can write. So here b square minus 4ac, what was the value we were getting? That is greater than 0, right? So you can check that. So here we got the solutions. We said there will be so number A. So here you will get uh, two real roots and two distinct. Okay, two real roots and two distinct. So say this is a x and this is a time. So in this you will see there will be two characteristics. One will be a left running, right running, one will be a left running characteristic. So you will get two characteristics. Okay. There will be two characteristics. Will be two characteristic curves. Two characteristic curves. Okay. Now about the solution type to this hyperbolic PD, solution type will be wave-like. Okay. So what do you mean by wave-like solution? Is that suppose you are plotting t as a function of x, then you may get a wave-like nature of the solution. Okay. It can be like this or it can be any wave nature, sinusoidal kind of. Okay. So we know that now it will get a solution of this nature. Next, boundary conditions. Okay. So in this case, we need only boundary condition for incoming waves. So say you are looking at x and time t, and you have this left running or right running curves. Okay. Now you will have these two characteristic curves, and suppose this is our point under consideration. Uh, then you see at x, so incoming waves only you need to give boundary conditions. So for example, this is the incoming waves. Okay, but if you cut the domain, or you extend this, or say that if this is the x domain, here x is equals to L and x is equals to, or it is from x is equals, or here you say x is equals to some minus L by 2, then here we need to have a BC, boundary condition 1. But here we cannot give BC. Still, this is a boundary point. This is the end point at this time. So we need not to specify here BC, no boundary condition. But here we need a boundary condition here. We need a boundary condition here. BC needed. Okay. So and let me draw, say that this is the only L by point, some minus L by 4, say. So boundary condition 1, and this will be a boundary condition 2, because you have del 2 T del x2. So we need two boundary conditions, two time boundary conditions. Okay. So at T is equals to 0, you have to specify the temperature T or its derivative. These two values you will have to specify at the bound initial condition T is equals to 0. For T and its gradient has to be specified. Okay. So in general, we can write BC is for incoming waves. Incoming waves are specified, and no boundary condition, no boundary conditions for outgoing waves from the domain. Okay. Now domain of influence. Domain of influence. So here, as we said, there are two characteristics. So for this point under consideration, the information is coming only from this region. Okay, no information is coming from any other region. So this region where from the information is coming is called as domain of dependence. Domain of dependence. And other region outside this is a domain of influence. This region is a domain of influence. Domain of influence. Okay, so any value of I will affect any value at this point. Okay, but the value of the at I is only affected by the values coming from this region. Okay. So if you are designing any scheme, then you have to make sure that the contributing neighbors should be coming from this domain of dependence. Okay. The same thing here. Domain of influence and domain of dependence. Okay. So while designing a scheme, the point or node value under consideration should have contribution from from the neighbors coming from the region of dependence, from the region of dependence. Okay. Also, this can be a forward in time. Okay, forward in time, or you say marching in time. Marching in time in a forward direction. So marching in time, like scheme should be there. And again, if these situations are there, in those cases, you may face a problem of stability. Again, stability is a concern. So for both the problems of parabolic and hyperbolic nature, stability is a major concern. And again, in hyperbolic case, boundary conditions are very complex. They create a lot of problems, issues, because we have to always see which is the incoming wave and which one is the outgoing wave. Okay. So next type is elliptic PD. Elliptic PDs are very nice. Elliptic PDs. The example of elliptic PD is a Laplace equation. Laplace equation. Laplace equation is del 2 t del x2 plus del 2t del y2 in a two dimension. Okay. Also, it can be a Poisson equation. Poisson equation, which can be written as Laplace equation is equals to, so non-homogeneous part will be a function of some x and y. Okay. So these are the specific examples. So let us consider Laplace equations. Del 2t goes to 0. Now we said number one, here the solution. Now we are talking about x and y. Okay, so domain is like this. So in this case, how many, what is the solution? B square minus 4ac, B square minus 4ac greater than 0, isn't it? It is a greater than 0 case, less than 0 case. So we have uh, imaginary roots. Imaginary roots means we do not have, we have imaginary characteristics, so no characteristics. So no characteristics. No characteristics. Okay. There is no characteristic available in the elliptic type. The solution of the elliptic type, the solution type, it is called as equilibrium solution. Equilibrium solution. What does it mean by equilibrium solution? Is that suppose in this domain you have some boundary conditions like 0, 100, 0, and say 0. Then in this case, the solution will try to match the boundary condition you have specified. Okay. It will try to match the solution you have specified. Okay. So the effect of the boundary conditions will be felt everywhere immediately, so that the solution at this point will try to adjust with the effect coming from the far away, value. It will immediately, the effect will be immediately transferred. There is no time like evolution. Okay, so there is no time like evolution, that I'll write later. So third, let me write third about boundary conditions. So del 2t, it is a del 2t del x2. So 2bc on x and del 2t del y2. So 2bc's on y. Okay. So suppose this is a x is equals to 0, we need a boundary condition. X is equals to L, we need a boundary condition. Y is equals to 0, we need a boundary condition. At y is equals to L, we need a boundary condition. So two boundary conditions are needed. At x is equals to 0, one boundary condition. At x is equals to L, one boundary condition. At y is equals to 0, at one boundary condition. And at y is equals to L, one boundary condition. Okay. So in simply writing, on x is equals to 0, BC1, x is equals to L, BC2, and y is equals to G. This is y is equals to 0. This is BC3, and here will be BC4. This is a y is equals to L. This is whole is a y is equals to L. This is y is equals to 0. This is x is equals to 0. This is x is equals to L. So we need 4 boundary conditions on every surface, boundary is given. Next, about domain of dependence. Okay, so domain of dependence and influence, as there is no characteristic, we say that the domain of dependence is a complete domain. So this complete domain is a domain of dependence. There is no characteristic. So any point in this, it will have a contribution from all the neighboring cells coming from all directions. Okay. So any point here, it will have effect from neighboring coming from, okay, in the domain. In the domain. So any point you will have a neighboring effect. So domain of dependence is a whole domain. Whole domain. This is a domain of dependence. And influence also. Domain of dependence, and influence. So at every neighboring point, every other point will be affected. So this point will affect the neighboring points. So influence and domain of dependence, they remain same. Okay. So the while designing, you need to take care of. So here there is no problem. Okay, so we do not have to worry that where from the information coming. All the neighbors while designing a scheme, all the neighbors, all the neighboring node values will be considered influencing the value under estimation, under calculation. Okay. There is no time like evolution. Okay. In the previous cases, in case of the hyperbolic and parabolic PD, we see that there is a time like variable. So there is a time like evolution in time. Solution was evolving in time. Solution was evolving in time. But in case of elliptic case, there is no time like evolution. So there is no time like variable. So there is no time like variable. Time like variable. So no marching in time. Marching in time or space. Okay. Sometimes in parabolic problems, instead of t, you can have a x also. Instead of t, you can have a x also. This the same equation can also be written as del t del x alpha del 2t del x del y2. Okay. So any variables can be there. Now y is acting like a space variable. This is acting like a space variable. This is acting like a time variable. Okay. So it is a marching in x. Okay. Marching in x. Here marching in t. Marching in t. So marching is a main characteristic of this hyperbolic and parabolic. Either it may be marching in time or it may be marching in space also. But since in hyperbolic cases there is never a term like uh, this time or space marching, evolution kind of, then there is no marching in time space, in time and space. Okay. So these are the certain characteristics of the this standard PDs available to us. Now, given this PDs, now we would like to now know the solutions. Okay. Our objective, main objective is to get the solution of this PD. You understood this? This classification, their characteristics. Parabolic PDs will have one characteristic. Solution type will be a diffusion type. Boundary conditions, you need boundary conditions at x is equals to 0, x is equals to L, and at t is equals to 0, you need bound all the values, special values should be given. And then domain of dependence will be a region below the characteristic curve will be domain of dependence, and the rest of the region above the characteristic line will be a domain of influence. Okay. Now these things need to be considered while designing a scheme like forward scheme or backward scheme. Those are schemes. Those are different schemes. So at least I hope that you have heard about this finite difference, finite backward difference, forward difference, central difference. Okay. In hyperbolic cases, there will be two characteristics. Solution will be wave-like solution. Boundary conditions, you need boundary conditions for incoming waves, outgoing waves, you do not give boundary conditions. For incoming waves, you give, but and at t is equals to 0, you need all boundary conditions for space. Domain of influence is the region covered by the two curves, and the domain of dependence will be the region covered by these two curves, and the above region will be domain of influence. And the solution will be marching type of. Okay, so scheme should be marching type of schemes. Marching type of strategies has to be, and here you will get a problem of stability. Here a stability again is a problem. Here is no problem of stability. Okay, no problem of stability.